FeatureScript is the native language in Onshape. It is not a macro language that you may have used in other CAD systems. As we discussed before, it only interacts with a Part Studio. Custom features act like any other feature in the feature list, which means they execute chronologically, are affected by the rollback bar, and can be modified by configurations. Because of this, it executes automatically when the Part Studio is rebuilt, whereas a macro would need to be rerun separately. It is more secure and doesn't have the ability to transmit viruses or steal data. It also never needs to be upgraded, when macros frequently break on upgrade. FeatureScript is designed to look and feel familiar to anyone who is used to working in the C family of languages such as C, Java, or JavaScript. It is whitespace insensitive, and statements always end with a semicolon character. While programs in most other languages are defined in files, FeatureScript is defined in modules. A Feature Studio or a Part Studio are examples of modules. A module consists of top-level declarations. Examples include imports, global constant declarations, type definitions, and function declarations. Declarations are important, but the bulk of the code is composed of statements. Statements are instructions to perform a certain action. They often involve expressions, which are portions of the code that evaluate to a value. For example, the sum of two variables, a string literal or a function call, are considered expressions. You can think of a custom feature as a function declaration that contains a set of statements, many of which are made up of expressions. All identifiers follow common programming conventions. It can start with a letter or underscore and contain any combination of alphanumeric and underscore characters. Upper and lower case letters are distinct and special characters are not allowed. Variables and constants are very commonly used in FeatureScript. Variables can be changed throughout the duration of the script, but constants will throw an error if the script attempts to change it after assigning an initial value. Start from the basic Q custom feature we created in a previous video. Declare a variable and name it X. You can end the statement with or without a value. Set the value to 3. Multiply the vector for corner 2 by X. Now, if you enter 1 in the feature dialog, each side of the cube is 3 inches. The printline function can come in handy when you are trying to troubleshoot the values of variables. Create a printline function and set it to show the value of X. Turn on the monitor for the Part Studio in the top right pull-down. The FeatureScript Notices panel shows the value to be 3. The Part Studio monitor allows you to evaluate committed changes in the FeatureScript notices without having to change back to the Part Studio. Now declare a constant named y with the value of 4. Add another printline function to display y. Now it reports the value of y in the FeatureScript Notices panel. Try setting y equal to 5 after the initial declaration. This causes an error message because it cannot assign a new value to a constant. Each value in FeatureScript has one of several standard types. There is only one type of number that represents integers, decimals, and even infinity or negative infinity. Certain number operations are not supported, such as dividing 0 by 0 or operations that would result in imaginary numbers. Boolean is a true or false value. String represents any sequence of Unicode characters. You can define them with single or double quotes. Arrays are a list of values enclosed with square brackets. There is no restriction on what type each value in an array has to be. They can all be different. Maps are similar to arrays, but are a list of key value pairs and are enclosed in curly braces. Maps are often used for custom types, like a value with units, which has a number and a unit. The definition .side length is an example of this. Undefined is a special value and type that arises in situations like an uninitialized variable or the result of looking up a map key that doesn't exist. Finally, a few more specialized types are the function, box, and built-in. The function type allows you to pass an anonymous function as a value. The box type allows you to pass by reference, which means the callee can put a new value into the box and the caller will see the new value. Built-in is something you can't see directly inside, but can be used with the standard library functions. We will see a few examples of why you would use the built-in type in a future video. In this video, we discussed how variables and constants behave inside of FeatureScript and the various types available. There are several operators available for use in Onshape. There are common number operators such as addition, subtraction, multiplication, division, and others. In the cube custom feature, we previously multiplied side length by x to define corner 2. If you are not following the videos in order, copy the cube document in the key takeaways for this video. Before we make changes, comment out any remaining printline functions. Move the definition .side length into the definition for x. You could add further operators to the value of x, such as dividing by 2. Now, with 1 as the side length, the sides are 1.5. There are also comparison operators that compare two values and return a Boolean or true-false result. Boolean values are important for if, for, and while statements. We will go into detail in a later video. Comparison operators include equality, greater than, less than, and others. The equality comparison is always two equal signs because a single equal indicates you are setting a value. FeatureScript, unlike C, does not interpret 0 as false and non-zero as true in Boolean expressions. Along the same lines, there are the logical operators. They allow you to combine several Boolean expressions and return a Boolean for whether the entire expression is true or false. Like most other languages, FeatureScript does not evaluate the second operand unless it needs to. The not operator returns the opposite of the original value. Adding a not operator to the front of a comparison changes it to true instead of false. Another operator concatenates strings together using a tilde. Anything that is static text needs to be surrounded by single or double quotes, while variables and constants should not have quotes. In the cube custom feature, change the name of x to entered size and set it to equal the side length. Create and set the variable's size limit to 5 inches. We will discuss more in a later video the importance of units. Add another printline function, and within the parentheses, add a concatenated string displaying the values of entered size and size limit. The result is not very readable because values with units are stored as maps. We will learn more about maps in another video. Use the function toString to make it readable when printing. Finally, the conditional operator takes in a condition, that is, a true or false statement, and returns a different value based on the result. Modify the cube custom feature so that if the user inputs a length that is too large, the code overrides it with an acceptable value. Create another variable named cube size. Set it equal to a conditional operator that checks whether entered size is larger than the size limit. If it is true, the value is size limit. If it is false, the value is entered size. Multiply the vector in quarter 2 by cube size instead of entered size. Test the custom feature. If you input anything above 5 inches, the cube does not get any larger. Every variable has exactly one standard type, but can also have a custom type that gives it a more specific purpose. In the standard library documentation, there are many custom types already defined. For example, a vector is a type of array, lines and queries are maps, context is a built-in, and many others. One custom type that is very important to understand is value with units. Many operation functions in the standard library require value with units in its definition to define distance. To add units to a number value, multiply as appropriate by the unit. There is a full list of available units in the standard library documentation. Compound units such as inches per second are also valid and defined with the appropriate mathematical operators. You can add two values with different length units, such as meters and inches. Adding incompatible units is invalid and throws an error. Multiplication and division affect both the value and the unit. For example, if you multiply two values with length units, the result is a value with area units. If you divide two values with the same unit type, the result is a unitless number because the units cancel each other. You can also raise the power of a unit for area and volume assignments. We assign the value for size limit and the values for the vectors in the f-cuboid function. Both corners in the f-cuboid function need to be vectors where each value is a value with units. The first corner is multiplied by inch because the vector doesn't contain units. The second corner didn't need it because the cube size variable already had units. Because of finite precision arithmetic, you may get unanticipated results when printing or comparing values with units. Previously, we used the toString function to print the values of entered size and size limit, but it listed it in meters instead of the inches we assigned. Value with units is a map that always converts the values you put into it and stores them in metric units. To show in inches instead, remove the toString functions and divide by the correct unit. This creates a unitless number, but the value is converted appropriately. The result might be slightly off due to it being a floating point number. Use round to precision to get the desired result. The same happens in comparisons, giving a false result when it is actually true. To avoid this, you should always use tolerant equals to compare values with units. Enumerations allow you to specify a fixed set of named options. An enum is called with its type and value separated with dot notation. Many functions in the standard library are defined with enumerations. For example, the debug function has an enumeration that allows you to assign a color for the highlight. Add a debug function below the f-cuboid function. Debug takes in arguments for the context, value, and optionally color. Set the value to Q everything and color to debug color.green. While editing the feature dialog, it highlights everything in the context of the model in green. A variable or constant's type is unconstrained and can change based on the values assigned to it throughout the code. When declaring a variable or constant, you can constrain its type with the is operator. This is useful to ensure you are not incorrectly assigning the wrong types of values in the code. When you constrain the type, it is required that you also add an initial value. Remove or comment out any remaining printline and debug functions in the Q custom feature. Add is value with units to the declaration of cube size. It runs correctly because it is correctly constrained. If you try to remove the value for cube size, the FeatureScript Notices panel shows an error. Once set, FeatureScript enforces the assign type and errors if an incorrect value is entered. Assigning a custom type to a value does not change its standard type. Cube size is a value with units, which is a special type of map. If you change the cube size constraint to map, the value is still valid because a map is less specific. You can also check the type of value with the is constraint. Create the statement var test size equals cube size is value with units. Use a printline function to display the value as true. It is common to use this operation in function declarations to ensure the arguments are a specific type. We will learn more about function declarations in another video. Remove or comment out these lines after testing because they are no longer needed for the feature. If you need to cast a value as a new compatible type, you can use as. In a new line, set cube size to cube size as map. This causes an error in the feature. It doesn't know how to multiply the numbers in a vector with a standard map. Remove the line in the code to repair the feature. Functions and operators can be overloaded to complete different actions depending on the type of argument. Functions are overloaded when you use the same function name to define different functions with a related purpose. For example, we used toString in a previous video to display the result of a value with units in a readable format. The standard library contains a family of functions called toString that each take different input types and return a string representation appropriate for that value. FeatureScript always matches the arguments to the most specific function implementation. Value with units is a specific type of map, so FeatureScript chooses the value with units implementation. Open the Q custom feature. Cast size limit as a map. Now, print size limit using toString. Size limit prints as a map because it is no longer tagged with the more specific type. The comparison also errors because you cannot compare a value with units with a regular map. Remove the map tag from size limit to repair the feature. You can also overload operators. An example of this in the Q custom feature is the size limit. When you multiply a number by a unit of measure, there is an overload on the operator for multiplication that automatically returns a value with units type. Another example of an overloaded operator is completing math on vectors. Without overloads, the addition of two vectors would cause an error. The addition operator is overloaded in the standard library to add each component of the vector separately to give a predictable result. There are other similar overloads in the standard library to ensure you get expected results when completing math on many different types of data. You can create custom overloaded functions and operators as top-level constructs. They are usually combined with custom types. If, for, and while are all branching statements. This means they segment an area of code that only executes under certain conditions. If is a one-time execution, whereas for and while statements loop until the condition is no longer true. If statements are similar to the conditional operator we discussed in a previous video. It has a condition and actions to complete whether the condition is found to be true or false. The else part of the statement is optional. It is valid to have an if statement that only contains actions for if the condition is true. In the Qt Feature Studio, remove or comment out any remaining printline statements. If you are not following the videos in order, start a new if statement below the entered size declaration. Press enter to autocomplete. Add the comparison entered size equals 5 inches as the condition. When doing a comparison, you must use two equal signs, otherwise FeatureScript thinks you are trying to assign a value. Press Tab to move inside the if statement. Add a printline function to print success in the FeatureScript notices if the entered size is 5 inches. In addition to the autocomplete shortcuts, Feature Studios can create context-aware code blocks with the Insert Snippet tool in the right-click menu. Add an else statement to capture when it does not meet the condition. Add the printline function to print failed. Commit and run the feature in a Part Studio. Enter a size of 5 inches. Success prints in the FeatureScript Notices panel. Failed prints for any other number. You can put in more than one condition separated by and or operators. Change the condition for the if statement to entered size is greater than or equal to 5 inches and entered size is less than 10 inches. Now there is a range of values that can return either success or failure. Now we can use this to control the cube so that it does not function when it is outside the range. Comment out or remove the declarations for cube size and size limit. Move the fcuboid function into the if statement. Change the definition for corner 2 to reference the entered size. The cube generates with the appropriate size only when it is within the range. Otherwise, it prints failed. Ideally, you want to add an error message that makes it more clear why the feature is failing to the user. For loops use conditions, but unlike if statements, they keep looping until they are no longer true. In order to do a for loop, you need to define a variable that sets an initial value, condition, and an increment, all separated by semicolons. Create a for loop. Declare variable I and set it equal to 1. Use the condition less than 10. And use I plus equals 1 to increment it by 1 in each loop. This is what is called an assignment with operator. This means I plus equals 1 is the same as I equals I plus 1. Inside the for loop, use a printline function to print the value of I. When you run it, you can see that it prints each number on separate lines in the FeatureScript Notices panel. We can use the for loop to create a pattern of cubes. Comment out or remove the previous loop. Create a for loop inside the previous if statement. Use the same range for I. Since we are calling the operation in a loop, we cannot leave the ID of the operation at the default. If you do, you receive the error duplicate ID in context. Any function that operates on the context of the Part Studio needs to have a unique ID. Add I to the ID of fcuboid after the root ID, but before the cuboid1 string. We will discuss more about formatting IDs properly in another video. Right now, the custom feature will run, but each cube is created on top of each other. To make each cube coincident with the last, we need to adjust the locations of corner 1 and 2. Change the x component of each vector to make the cubes coincident. The variable I is iterating with each loop, so we can use a formula that incorporates it in the vectors. For corner 1, change the x component of the vector to I-1 and multiply the entire vector by the entered size. The inch units are no longer needed because entered size contains units. This means for the first iteration the vector is still at the origin, but additional iterations add the entered size times I to the x component. Multiplying the entire vector by the entered size does not affect the y and z components since they are 0. Corner 2 should start at the entered size and increment by 1 for iterations, so it is only necessary to input I for the x component of the vector. Now the Part Studio generates 9 cubes. All of them are coincident with the previous. While loops are similar to for loops, but just require a single condition that is evaluated each time it loops. You must execute an increment or action inside the body of the loop that eventually causes the while statement to no longer evaluate to true. Otherwise, the feature infinitely loops and never completes. To change the for loop to a while loop, first initialize I in a separate declaration. Then set the condition I is less than 10. Inside, at I plus equals 1 to iterate it. In the Part Studio, the result is exactly the same as the for loop. Maps and arrays can contain many different types of data. They could have text, numbers, booleans, and even other arrays or maps as values. An array is a container where values are accessed by index. FeatureScript arrays are indexed starting from 0. In this example, index 0 is 4, index 1 is 3, index 2 is 6, and index 3 is 7. In the Cube custom feature, remove or comment out any remaining printline functions except the warning for if the feature fails. Create an array named PositionArray with the values 15, 5, 40, and 27. Create a printline function to show the value at index 1. The FeatureScript notices appropriately shows the value of 5. Create a for loop to cycle through the array. Use var p equals 0 as the starting value. P is less than the size of PositionArray as the condition, and p plus equals 1 as the increment. The size function automatically finds the upper limit in the array. For each loop, execute printline PositionArray at position p. The result prints every value from the array as a new line. You can also use var p position in PositionArray to iterate the loop. In this syntax, the first variable is always the index and the second one is the value. It gives the same result but requires less code. Instead of making all the cubes coincident with the previous one, we will use the PositionArray to control the x-coordinate of corner 1. Replace the while loop with the for loop so we can use the array to control the locations of the cubes. Change the feature ID to use p. To change the positions in the x direction, we need to manipulate the x-coordinate of the vectors for the corners. Change corner 1 to position 0, 0, and multiply by inch. Corner 2 is dependent on the position and the entered size. Change corner 2 to add position and entered size together for the x-coordinate. Multiply the position by inches because the array does not contain units. Instead of multiplying the entire vector by entered size, add it into the components for y and z. Commit the changes and switch to the Part Studio. Each of the cubes starts at one of the positions from the array. A map is a container where values are accessed by key. All of the standard library operation functions used to create geometry in the 3D model space take in a map as one of its arguments. The values are put inside curly braces with a colon between the key and value pair. Keys and values may be of many different types in the same map, making maps an extremely flexible data container. Define a map called CubeMap. Use it to replace the map argument in the fcuboid function. To retrieve a value in the map, you can use dot notation to call the key. Create a printline function to show the value for corner 1. Use toString to print the value in a readable format. If you need to iterate through all the key and value pairs in a map, you can use a for loop. Use the syntax var key value in CubeMap and use a printline function to print each key and value pair. comment out or delete any remaining print line functions for clarity. Iteration through a map is deterministic. It shows in the same order every time the custom feature is run, but it does not necessarily iterate in the order entries are added. The Utilities section of the standard library documentation contains functions for working with arrays and maps. This includes functions that can search for values, sort, resize, append, and combine. Functions are a set of statements bundled together. For example, there are the standard library functions. We have already used the printline and fcuboid functions in the Cube custom feature. You can call a function from inside other functions, such as a custom feature, by listing the name and enclosing any arguments inside a pair of parentheses. Functions are declared as a top-level construct. It starts with the name of the function and a list of arguments it needs to execute. The names of the arguments are merely placeholders and do not need to match what is sent when the function is called. The order is what is important when there are multiple arguments. You can also define what type is required for each argument, such as number or string. Inside of curly braces are a series of statements that make up the function. Most functions have a return statement to return a value. In the Cube custom feature, create a new function that doubles any input number. It takes in a number for the argument. Inside the function, add a return statement to return n times 2. You can also apply constraints to the return value by adding isNumber to the return value or returns number in the declaration. Use the double function on the upper limit of the if statement. Now you can enter any size between 5 and 19. A function that returns a true or false value based on a series of one or more Boolean expressions is called a predicate. The predicate only returns true if all the expressions it contains are true. Move the comparison to a predicate function. Name it correct size. It takes in one argument for a value with units. Add expressions for each of the comparisons. Call the predicate from the if statement. Now that the predicate controls the comparison, you could reuse it in multiple parts of the code if you need to. If you are defining a function that should only execute if the arguments meet certain conditions, you can add a predicate within the precondition. Preconditions are inserted between the arguments and the body of the function. You can define it as just one statement or a block with curly braces. The entire user interface of a custom feature is defined by the feature precondition. In the Cube custom feature, the isLength function ensures the type of the inputted value. If you put a text value, the precondition fails and the function does not execute. There is another special type of function called a lambda or anonymous function. These functions are not declared at the top level and are passed as a value. In the standard library, they are frequently employed as an argument to a higher level function. One example is the sort function. It takes in two arguments, one for the array and the other is a lambda to define how they should be compared. In the Cube feature, use the sort function to sort the position array in ascending order. Create a variable named sorted array and set it equal to the result of a sort function. Enter position array for the array to sort. The second argument is a lambda function. Lambdas are declared with the word function instead of a name. A sorting lambda takes in two arguments, a and b. For the body, subtract b from a. If the result is positive, it swaps the numbers in the array. This results in an ascending list. It automatically iterates until the entire array is sorted. Create a print line to see the sorted array. Remove any other print line functions for clarity. The newly sorted array is in ascending order. Imports allow you to reference other tabs and documents within Onshape. You can import other Feature Studios, Part Studio geometry, and other data contained within a document such as a CSV or image. Every new Feature Studio starts with an import of the geometry.fs, which imports most of the functions defined in the standard library. Importing all of this information can have a negative impact on the performance of the Feature Studio. If you do not require everything, you can change it to common.fs, which contains the most commonly used functions. Imports can have one of two types of references. They can either reference a tab within the workspace or a tab in a version. Just like with other references in Onshape, workspace references update automatically, but are only available if they are contained within the same document and branch as the Feature Studio. When working on complex projects, it can improve readability to separate out subfunctions or data tables into their own Feature Studios, then import them into the main studio. Open the Cube Custom feature. When you are using a function that is imported, hold Control or Command on a Mac and select the function to open it in the source. Go to the source of the printline function. It automatically opens the source code and navigates to the correct function. Notice that the function is exported. Only the exported symbols can be imported into another script. Create a new Feature Studio in the same document as the Cube feature. Add a function to it named printWithUnits. This function has the flexibility to print any unit you choose. It takes in 3 arguments: the current value, unit, and unit label. It then prints a line showing the value in the correct units with the label of your choosing. Go back to the original script in the Other Feature Studio tab and select Import. Under the current document, select the printWithUnits Feature Studio. It adds a new import with the UID for the tab and version. This is a workspace reference, but it still enters a UID for the version. Add a line to call the printWithUnits function. Choose entered size as the value and inch as the unit and label. Comment out or remove any other print line functions for clarity. The value appropriately prints in the FeatureScript Notices panel. Depending on the numbers and units you entered, the result may be slightly off. This is due to the imprecise nature of floating point numbers. The round-to-precision function easily corrects the printed value. Once committed, the custom feature automatically updates with the new result because of the workspace reference. Try converting the entered size to centimeters. This is a simple example, but can be valuable when designing complex custom features that would benefit from being segmented into several feature studios.